Hello everyone, I am Dr. Sadanand Kumar, Assistant Professor, Department of Physics, AJ Institute of Engineering and Technology, Mangalore. In this session, I am going to discuss some concepts of the quantum mechanics. Contents of the discussion: blackbody radiation spectrum, Planck's radiation law, wave-particle dualism, de-Broglie hypothesis, matter waves, and some problems related to the concept. So when we think of a blackbody radiation spectrum, we should know what is a blackbody. A body which is capable of absorbing all the radiations falling onto it, and heated to a certain temperature, it will re-emit the radiation. Such a body is called blackbody. You can think of example for a blackbody, any body which is coated with a black material, or happen to be example for black body. So a material coated with a black absorbs nearly 98 to 99% of the incident radiation. That's happen to be example for black body. In principle, a black body must absorb electromagnetic waves of any given wavelength. With this property, the scientist Kirchhoff stated that black body should radiate electromagnetic waves of all wavelengths when heat is supplied to it. Due to this concept, a spectrum of a black body should contain completely the entire electromagnetic spectrum. So, energy radiated by a black body is distributed in the entire range of electromagnetic spectrum is called blackbody radiation spectrum. Now, in order to study the energy distribution in a blackbody radiation spectrum, in the 1895, the two scientists Leumer and Wien designed a special type of body which possesses features very close to a black body. They conducted the experiments by heating a black body to higher and higher temperature and studied the spectrum of radiation issued by a black body. They found the spectrum did include wide range of wavelengths. The experimental parameters such as intensity and wavelength is taken and plotted a graph of intensity versus wavelength from the experiment. And this graph is drawn for different temperatures. Intensity versus wavelength graph is plotted for different temperatures. The plot of that graph is shown in the slide. In this graph you can see the ultraviolet region and infrared region. So ultraviolet region, that will be the shorter wavelength region, and infrared region is the other region, that is longer wavelength region of the spectrum. Okay, by looking at this spectrum, one can draw the following conclusions. The first point, they concluded there are different curves for different temperatures. That's quite obvious. For different temperature, different curves are there. The second one is there is a peak or a spike for each curve. That means peak represents highest emission at a particular wavelength in a given temperature. And this particular conclusion is termed as Wien's displacement law. That means lambda m into T is equal to constant, where lambda m is the maximum radiation emitted at a particular wavelength for a given temperature. And the third point they concluded is there is a peak shift towards shorter wavelength side with the increasing temperature. That's also seen the peak or the spike that will be shifting towards lower wavelength side as the temperature is increasing. Right now, to explain the energy distribution in the blackbody radiation spectrum, the various theories have been put forward. So in 1896, Wien tried to explain the energy distribution in the blackbody radiation spectrum through the relation between the wavelength of emission and the temperature of the source. And he has given the theoretical equation that is the expression for energy density in the wavelength range of lambda and lambda plus d lambda is u lambda d lambda equal to C1 lambda power minus 5 exponential minus open bracket C2 by lambda t close bracket into d lambda. This is the equation he has taken and tried to explain the energy distributed in the shorter wavelength as well as the longer wavelength region of the black body radiation spectrum. So he is able to explain only the shorter wavelength region of the spectrum, but when it comes to the longer wavelength region of the spectrum, he was not able to explain. Therefore, the Wien's law fails to explain the entire black body radiation spectrum, how exactly the energy is distributed in it. So, after the failure of the Wien's law, the scientist named Rayleigh Jeans, who came forward and he gave his theoretical idea to explain the energy distribution in the black body radiation spectrum, and he has considered the theory based on the Maxwell's law of equipartition of energy, and it says that an average energy kT should be assigned to the each mode of vibration, which means if at all there is a particle which is present in a black body, when the heat is supplied to it, it will start vibrating. So in such a situation, for each mode of vibration, average energy of kT should be assigned to it. According to the Rayleigh-Jeans law, he has given the mathematical relation in the wavelength range of lambda and d lambda plus d lambda. So expression for energy density is u lambda d lambda equal to 8 pi kT by lambda power 4 into d lambda. But theory is able to explain only the longer wavelength region of the black body radiation spectrum, but when it comes to the short wavelength region, the theory unable to explain the energy distributions, which means the Wien's law is able to explain the short wavelength region, but Rayleigh-Jeans law is able to explain the longer wavelength region of the spectrum. But together as a single equation, it is not able to explain both the region of the black body radiation spectrum, which means both laws are failed to explain the entire the black body radiation spectrum, in the sense energy distributed in the black body radiation spectrum. With the failures of these two laws, in 1900, Max Planck gave his theoretical equations to explain the energy distribution in a black body radiation spectrum. And his idea, he has incorporated his idea that the probability of emission of radiation that decreases as its frequency increases, so that the curve slopes down in the high frequency region. So what happens if you consider these assumptions? It necessitates that assume the oscillators in the black body can have a discrete set of energies, which means energy possessed by these oscillators are not a continuous one. It is quasi-continuous or discrete set of energy values. So Max Planck has assumed, or he has made some assumptions to explain the theoretical relations which is required to explain the energy spread in the black body radiation spectrum. The first point is atoms in the walls of a black body behaves like simple harmonic oscillators, which means they will oscillate like a simple harmonic oscillators. So obviously once it oscillates simple harmonic oscillators, the energy of these oscillators in a black body is quantized, which means E equal to NH nu. So where n is an integer, it will take the value of n equal to 0, 1, 2, 3, 4, etc. And nu is the frequency of oscillations, and h is Planck's constant, of course. The third point, an oscillator may lose or gain energy by emitting or absorbing radiations of frequency nu, and its value is given by nu equal to delta E by h, where delta E is the difference in the value of energies of the oscillator before and after the emission or absorption takes place. Now, by considering these assumptions, Planck has derived the expression to explain the energy spread in a blackbody radiation spectrum. So, that expression is the expression for energy density in the wavelength range of lambda, and lambda plus d lambda is given by 8 pi hc by lambda power 5 into 1 by e power hc by lambda kt minus 1 into d lambda. And this equation is called as Planck's law of radiation, or Planck's radiation law. Which means Planck's law is capable of explaining both short wavelength region and long wavelength region of the blackbody radiation spectrum by taking this particular expression. You can see this equation here by taking this particular equation. Next concept is wave particle dualism. Dual nature of radiation, which means a radiation which behaves particle nature under certain circumstances, and the same radiation that show the wave nature under certain other circumstances. For example, in the case of X-rays, from the Compton effect experiments, X-ray radiation is scattered by an electron. This proves the particle nature of X-rays. Also, X-rays are diffracted by crystals, but diffraction is a wave phenomena. So, according to the wave theory, light waves leave a source with their energy spread out continuously through the wave pattern. And according to quantum theory, light consists of a stream of photons, each small enough to be absorbed by a single electron. And both these waves have a strong experimental support. Hence, one can think of light as having a dual character. Or radiation can have a dual character. I have given the example of X-ray radiations. It will behave wave as well as the particle nature. Likewise, according to this theory also, a light can behave as particle or the wave nature. Therefore, the light or the radiations can have dual character. The property of light of behaving as both a particle and a wave is called wave particle duality. Next concept is de-Broglie hypothesis. The de-Broglie has extended the wave particle dualism to the moving material particles. And according to him, material moving in motion which possesses a wave character. The waves associated with material particles are called matter waves or de-Broglie waves. Let us see the expression for de-Broglie wavelength. So what is the expression for de-Broglie wavelength? For this, let me consider a photon of frequency nu. Its energy is given by E equal to h nu. It's according to the quantum theory. Now, if I treat this photon as a particle of mass m which is moving with the velocity c, then according to the Einstein's mass inertia relation, the E equal to mc square. Since I have taken a photon which is treated as a particle, I can equate these two energies. Therefore, h nu equal to mc square. That's a simple rearrangements there. So, nu equal to c by lambda substituted. So, mc is equal to h by lambda. That means lambda is equal to h by p, where p equal to mc. That's a momentum of the photon. Therefore, lambda is equal to h by mv, where m is the momentum of a particle. So, this is the expression for de-Broglie wavelength for a particle. Now, if the electrons are accelerated by a potential difference of v volts, so that electrons acquire a velocity v, then the work done on the electrons is ev. As a result, the kinetic energy gained by these electrons is half mu square. Now, the work done in moving these electrons is equal to the kinetic energy of the electrons. Based on that concept, I can write the work done equal to kinetic energy equated EV equal to half mu square. In other words, 2 mev equal to m square v square. mv equal to square root of 2 mev. Or by using the deBroglie's concept, the lambda is equal to h by p, in other words h by square root of 2 mev. So this is the expression for deBroglie wavelength if the potential difference is mentioned in a numerical. Or same can be written as lambda is equal to h by square root of 2 m capital E, where E is the kinetic energy, because in the previous expression it is 2 mev. ev is the work done. We have treated that the work done is equal to the kinetic energy. Therefore, I can write the lambda is equal to h by square root of 2 me, where E is the kinetic energy term. So, expression for de-Broglie wavelength of an electron is seen. Next, characteristics of matter waves. Matter waves are the waves associated with the moving material particles. Matter waves produce interference and diffraction effects similar to the electromagnetic waves. The third point, the amplitude of the matter waves at a particular region and time gives the probability of finding the particle at the same region and time, which means amplitude gives information about the chance of finding the particle at a particular point and region. That means in sense that the point as well as the time. So chance of finding the particle at a given region and a time. The next point is the wavelength of matter waves is inversely proportional to velocity of the body. Therefore, a body at rest has an infinite wavelength, and one traveling with the higher velocity has a lower wavelength. Fifth point is wavelength of matter waves decreases with increase in mass of the body. So due to this, wave-like behavior of a heavier bodies is not very evident, whereas wave nature of subatomic particles could be observed experimentally. So these are the characteristics of the matter waves. Let us move on to some problems from the de-Broglie hypothesis. First problem, calculate the momentum of an electron and a de-Broglie wavelength associated with it if its kinetic energy is 1.5 kilo electron volt. In this problem, the given parameter are kinetic energy is given, it is 1.5 kilo electron volt, and convert this electron volt into joule, that is by multiplying with 1.6 into 10 power minus 19 coulombs. That's equal to 2.4 into 10 power minus 16 joules. So energy term is, got it, the Planck's constant is known, it's a given parameter 6.625 into 10 power minus 34 joule second. Mass of the electron is known, 9.1 into 10 power minus 31 kg, and unknown parameter is the momentum and also the de-Broglie wavelength. So in order to calculate the momentum, let me consider the expression for kinetic energy, that is E equal to half mu square, multiplying m either side, that is 2me, that is equal to m square v square, and also I took the 2 to the left side. So 2m equal to m square v square, where mu is equal to p, therefore p can be written as square root of 2me. Now just substitute the energy term as well as the mass term, mass value in the equation, so that the momentum is 2.09 into 10 power minus 23 kg meter per second. And the de-Broglie wavelength, of course, lambda is equal to h by p. So in this particular expression, it is lambda equal to h by square root of 2me. So if you substitute the value of h and p, you will get de-Broglie wavelength as 3.17 into 10 power minus 11 meters. The second problem, a particle of mass 0.5 mega electron volt per c square has kinetic energy 100 electron volt. Find its de-Broglie wavelength, where c is the velocity of light. So in this problem, the particle mass is given, but it is not in terms of kg. We need to convert it into kg. And also kinetic energy is given, it is in 100 electron volt. Convert electron volt to joule. So these are the two conversions you are supposed to do it. Then the unknown parameter is the de-Broglie wavelength. Since the energy term is given, we can use lambda is equal to h by square root of 2me. If the potential difference is given in the problem, then we can use lambda is equal to h by square root of 2mev. That's all the difference. Since the kinetic energy term is given here, we can use lambda is equal to h by square root of 2me, capital E. Okay. So let us do the conversion first of the mass as well as the kinetic energy. Mass term is 0.5 mega, m means mega there, electron volt by c square. C is the speed of light in vacuum. Just you substitute 0.5 mega is 10 power 6, electron volt is 1.6 into 10 power minus 19. That much value you are supposed to multiply in place of electron volt, and C is 3 into 10 power 8, square of that. So when you do this, please introduce the bracket concept, because otherwise you may miss the square term in C square. If you calculate this mass factor, it will be something like 8.9 into 10 power minus 31 kg you will get. And kinetic energy E equal to 100 electron volt, convert electron volt to joule, that is just multiplying by 1.6 into 10 power minus 19. That will be 1.6 into 10 power minus 17 joules. So de-Broglie wavelength as h by p, in other words h by square root of 2me. If you substitute the values, you will get answer as 1.24 into 10 power minus 10 meter, or 1.24 Armstrong. The third problem, calculate the wavelength associated with an electron raised through a potential difference of 2 kilovolt. Here in this problem, the potential difference V equal to 2 kilovolt, convert kilo into 10 power 3 volts, and lambda is unknown parameter. So since the potential difference is given, as I mentioned in the previous problem, you can use lambda is equal to h by square root of 2mev as the equation to solve this problem. So h is Planck's constant, known thing, and the m is the mass of the electron, is known thing, and V is given. Just substitute in the expression and you will get lambda is 2.75 into 10 power minus 11 meter. And today's session I will stop here. Thank you.